Welcome to the Curious Machine. Today, we're embarking on a deep dive into one of the most profound questions in all of science. How will the universe end? Forget merely understanding how it began. We're looking at the ultimate fate of everything, from the smallest particles to the grandest galaxies. Our mission is to unpack the leading scientific scenarios for the cosmos' conclusion, turning complex theories into understandable insights for you. So, let's explore this.
It's a fascinating journey, it really is. Delving into possibilities that range from the serene to the truly catastrophic. What's intriguing here is that while we often perceive the universe as vast and perhaps eternal, the laws of physics suggest it, like everything else, has a life cycle. And to understand its ultimate end, we first need to grasp a concept that's truly at the heart of it all: entropy.
Okay, entropy. Yeah, this concept can sound a bit intimidating. What exactly is it, maybe in simple terms, and why is it so crucial to how the universe might ultimately fade away?
Right. Think of entropy as the universe's inherent tendency toward equilibrium, a state where energy becomes uniformly distributed and, thus unavailable to do work. It's why your hot coffee cools down, right? Its heat disperses until it matches the room's temperature, becoming sort of inert. The energy isn't lost, but it's spread out, making it unusable to drive any process. The universe, in many ways, behaves similarly. It naturally tends towards a state where energy is so evenly spread out that nothing more can happen, no work can be done. This leads us to our first major scenario. This concept, also known as the Big Freeze or Big Chill, is the idea that the universe will reach a state of maximum entropy. All energy will be uniformly distributed, temperatures will equalize, and everything will cool down to near absolute zero.
That sounds incredibly bleak, just cold and empty. But what would this cosmic chill actually look like over truly immense timescales? What are the maybe unexpected consequences of such a complete loss of heat?
Well, in this scenario, trillions upon trillions of years from now, the last stars would burn out. They've consumed all their fuel. Planets would freeze, solid. Even black holes, those, cosmic vacuum cleaners, would slowly leak particles away through something called Hawking radiation. They effectively evaporate, leaving behind only a dilute, cold gas of photons and leptons. The universe would become this vast, silent graveyard. And the true existential chill isn't just the cold, it's the absolute lack of potential. No gradients, no change, no information transfer, just a flat, featureless equilibrium where nothing can ever happen again.
It paints quite a picture, a very still picture. But this assumes the universe is a closed system, right? Is that something scientists universally agree on, or are there different viewpoints about applying the rules of entropy to the entire cosmos?
That's an excellent point. It's not quite settled. Some prominent physicists, like Max Planck, argued that the concept of total entropy of the universe might not even have a precise meaning, because our understanding of entropy often comes from observing local systems, you see. Others, like Laszlo Tissa, point out that the universe isn't really in equilibrium right now, which complicates applying standard entropy definitions. And moreover, some theories suggest that gravity itself plays a unique role. It might actually prevent the universe from ever reaching a truly homogeneous equilibrium state.
That's fascinating, that gravity might prevent it. And you mentioned something counterintuitive, galaxies getting hotter when they lose energy. Could you maybe give us a quick analogy for why gravity might cause that?
Absolutely. Imagine a group of people dancing in a circle. If one person leaves the circle, the others might have to move a bit faster, maybe pull closer together to fill the gap. The overall system becomes a bit more energetic, more compact in a way. With gravity, systems like galaxies are bound together. If a star or maybe a gas cloud loses energy, perhaps radiating it away, it might fall deeper into the gravitational well. This makes it move faster, increasing its kinetic energy, which in a gravitationally bound system is kind of like getting hotter. It's an evolution towards more structured, heterogeneous states, not uniform ones. So yeah, this suggests the universe might never truly reach that perfect heat death.
Okay, so the quiet fade out isn't the only game in town. If the universe doesn't just quietly fade away, what's another dramatically different fate we need to consider?
Well, if the big freeze is a quiet fading, then the big rip is a violent tearing apart. This hypothetical scenario suggests the expansion of the universe could accelerate so rapidly that eventually everything gets torn apart. We're talking stars, galaxies, down to individual atoms, even subatomic particles.
Wow, the idea of everything literally ripping apart is incredibly vivid. What drives this extreme acceleration? How could it actually unravel everything we know?
Right. This scenario hinges on a specific, and I should stress hypothetical, type of dark energy called phantom energy. Unlike the dark energy we think we currently observe, which accelerates expansion but doesn't overcome local forces like gravity holding galaxies together. Well, phantom energy would be different. Its density would actually increase as the universe expands. Imagine stretching a piece of fabric. With phantom energy, the stretching wouldn't just get faster, the fabric itself would sort of become inherently weaker, more prone to tearing until it just shreds. What's truly chilling about the Big Rip isn't just the destruction, but how it turns gravity, the very force that binds everything, into the agent of its own destruction.
That fabric analogy makes it incredibly clear. So if this phantom energy is so potent, does it fundamentally change our understanding of dark energy as we currently perceive it? And what would be the sequence of events? How would this cosmic shredding actually play out?
Oh, dude, absolutely challenge our current understanding. If phantom energy exists, and that's a big if calculations, by a team led by Robert Caldwell at Dartmouth College, suggests the Big Rip could happen in roughly 22 billion years from now. And the process would be brutal. About 200 million years before the end, galaxies will be torn apart from each other by the expansion. Then, maybe 60 million years before, gravity would become too weak to hold individual galaxies together. They'd disintegrate. Just 3 months before the Big Rip, systems like our solar system would become gravitationally unbound, planets flying off into the void. In the final minutes, stars and planets themselves would be ripped apart. And in the last tiny fraction of a second, 10 to the minus 19 seconds, even atoms will be destroyed. The forces holding them together just get overwhelmed. The very fabric of space-time would rip apart.
That's almost unfathomable, the speed and totality of it. So this phantom energy idea, accelerating everything to oblivion, it's truly astonishing. What are the biggest hurdles, observationally, to either confirming it exists or maybe ruling it out?
The biggest hurdle is precision. It really comes down to measuring the expansion history of the universe very accurately. Current observations, from things like the Chandra X-ray Observatory and the Planck mission, they look at the expansion rate. They measure a parameter, often called W, which describes the pushiness or equation of state of dark energy. Right now, W looks very close to made at 1. If it were exactly made at 1, like a cosmological constant, the Big Rip couldn't happen. But a W is just slightly less than made at 1, even by a tiny amount, then phantom energy is real. And the Big Rip remains a possibility, although maybe pushed billions of years further into the future. The challenge is measuring W with enough precision to tell the difference between exactly made at 1 and slightly less than made at 1. It requires incredibly subtle measurements of how the universe's expansion is accelerating over time.
Okay, so we have the silent fade of the heat death and the violent shredding of the Big Rip. What about a third, perhaps even more dramatic possibility?
This leads us to the Big Crunch, which is essentially the exact opposite of the Big Bang. The idea here is if there's enough matter and energy in the universe, including dark matter, and maybe even dark energy behaving differently in the future, its overall gravitational pull could eventually halt the current expansion. And not just halt it, but reverse it. The universe would start to contract, falling back in on itself, collapsing into an infinitely hot, infinitely dense singularity, much like the state it, presumably began in.
So time would essentially run backwards, in a sense, everything coming back together. What would that actually look like for, say, galaxies and stars?
Exactly. A reversal. Some models suggest this contraction could begin maybe around 100 billion years from now, if it were to happen. First, you'd see galaxy clusters merging, pulling together. Then, galaxies themselves would collide much more frequently. Stars would get increasingly close, eventually crashing into each other. The whole universe heats up. That cosmic microwave background radiation, which is currently super cold, would start to heat up as it gets compressed and blue shifted. It would become so intense that stars would literally cook themselves from the outside in, bathed in this radiation, until they evaporate. In the final moments, the temperature would become so extreme that atoms and even atomic nuclei would break apart. Everything would get sucked into rapidly merging black holes, which then themselves coalesce. The entire universe becomes one giant fireball, ending in that final singularity.
That's intense. The imagery of everything collapsing into a fireball is certainly powerful, but does it just end there? Or is there a possibility of maybe a rebirth? What if that singularity isn't the end, but somehow a new beginning?
Ah, yes, this is where the Big Bounce hypothesis comes into play. It's a really intriguing idea. It suggests that after the Big Crunch collapses the universe into that singularity, maybe quantum gravity effects take over, preventing a true point of infinite density. Instead, the singularity could bounce, triggering another Big Bang and creating a new universe or a new cycle of our own universe. This implies a cyclic universe, one that perhaps endlessly expands and contracts, kind of like a cosmic yo-yo.
A cosmic yo-yo, I like that. So our universe might just be one in an infinite series of cosmic cycles. Are there other ideas about these repeating universes? What makes them distinct from just a simple big bounce?
Right, beyond that simple big crunch, big bounce picture, there are more modern and complex cyclic models. One is the ekpyrotic model. This suggests the Big Bang wasn't a unique starting point, but may be caused by the collision of two parallel branes, like membranes existing in a higher dimensional space. Our universe lives on one of these branes, and their periodic collision can be what we see as a big crunch, followed immediately by a Big Bang, sparking a new phase of expansion. The key difference here is placing our Big Bang within a larger pre-existing multidimensional setup.
Higher dimensions. Wow, that adds a whole new layer of complexity. And what about Roger Penrose's idea, the conformal cyclic cosmology? What's the core concept there?
Roger Penrose's conformal cyclic cosmology, or CCC, yeah, that's another fascinating one. It takes a different approach. In this model, the universe expands pretty much forever, maybe like the heat death scenario, until eventually all matter decays into massless particles like photons. At that point, Penrose argues, the universe loses any sense of scale. There's no time or distance measure left because only massless things moving at the speed of light exist. Mathematically, this infinitely large, cold, empty future state becomes geometrically equivalent to a hot, dense Big Bang state. So the end of one eon, or cycle, smoothly becomes the beginning of the next. Without needing a crunch or a bounce in the usual sense, it's a conformal rescaling. People have looked for potential signs of previous eons in the cosmic microwave background, like specific patterns, but so far there's no definitive detection.
These cyclic ideas are truly mind-bending, the universe potentially repeating itself. But what about a scenario that's even more, I don't know, unexpected, something that could just happen out of the blue?
Ah, this brings us to maybe the strangest one, the Big Slurp, or technically false vacuum decay. This is a possibility that sounds like pure science fiction, but is actually rooted in quantum field theory. The core idea is that our universe might currently exist in what's called a false vacuum state.
Okay, hold on. A false vacuum. If we're in a false one, what does that mean? What would a true vacuum look like? And why is this transition so dangerous?
Right. Imagine our universe's current energy state, like a ball resting in a dip on a hillside. It's stable there, sure, but it's not at the very bottom of the valley. It's not the absolute lowest possible energy state. The true vacuum would be that lowest point, the bottom of the valley, the state of minimum possible energy. Our current universe, the false vacuum, is stable, but maybe not ultimately stable. The danger is that because of quantum mechanics, specifically a phenomenon called quantum tunneling, a tiny bubble of that true vacuum could spontaneously appear anywhere in the universe at any time. It doesn't need a cause. It's a probabilistic quantum event. And if this bubble forms, it would then expand outward in all directions at the speed of light. As it expands, it converts everything it encounters, stars, planets, you, me, the very atoms we're made of, into this true vacuum state. And crucially, the laws of physics as we know them could be fundamentally different inside that bubble.
That concept, an instantaneous, unannounced transformation, that's quite profound, almost unsettling. What does this all mean for us then, here, now?
It's a truly chilling thought, isn't it? Because if it were to happen, it could happen instantly from our perspective. There'd be no warning. One moment, you're living your life, the universe is as it is, and the next. Everything within the bubble's path is gone, converted into this new lower energy state with potentially different physical laws. Some theories suggest fundamental constants could change inside the bubble, like the strength of gravity or the masses of fundamental particles. Everything would be different. There's a slight theoretical escape clause for very distant regions. It's theorized that regions of the universe very far away, maybe more than 4,200 megaparsecs, I think, might be safe. Because the expansion of space itself is faster than the speed of light at those vast distances, the bubble, expanding at light speed, couldn't actually catch up to them. But for everything within range, it would be an immediate and total annihilation, a complete rewriting of reality. Unlike the other scenarios that play out over billions or trillions of years, the Big Slurp is this sudden death possibility, an existential threat that could theoretically manifest right now, anywhere, without warning.
So we've taken quite a journey here, a deep dive into these cosmic possibilities, from the silent fade of the heat death to the violent tearing of the Big Rip, the cyclical dance of the Big Crunch and Big Bounce ideas, and the sudden, unsettling prospect of the Big Slurp. It really brings home how much we're still learning about our universe, doesn't it?
Absolutely. And What's truly profound, I think, is that while current observations maybe lean towards either a heat death or possibly a very distant Big Rip, the truth is we just don't fully understand the key players. The dynamics of dark energy and dark matter are still largely mysterious. We don't know for sure if the physical laws and fundamental constants we observe today will remain exactly the same over these immense future timescales. It means the universe's ultimate fate is still very much an open scientific question. It's a testament, really, to the ongoing cosmic mystery we're trying to unravel.
It's a remarkable thought, isn't it? To consider that everything we see and experience, everything that has ever been, could end in such distinct, dramatic ways. If our universe is destined for one of these incredible ends, what does that really mean for our place within its grand unfolding story? And maybe, how might thinking about these far future possibilities shape how we view our present moment in the cosmos?
Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.